Hello, I'm Tommy Mix, and in this video, I will be going over question number 5 in the 2014 Calculus BC exam. This is a non-calculator problem involving setting up integrals and in some cases solving them for a certain value. It is a BC problem but involves some AB topics. Okay, let's start with part A. So firstly, we should look at the graph. In the question, it tells us that R is the shaded region bounded by the graphs of y equals xe to the x squared, the line y equals negative 2x, and the vertical line x equals 1. So we can assume that this exponential line is xe to the x squared. This vertical line is x equals 1, and this line right here is y equals negative 2x. Part A asks us to find the area of R. So to find the area under or above a curve, you have to integrate. So we're going to have to integrate xe to the x squared and y equals negative 2x from and to a bound. Before we figure out what to put in the integral, let's start off with our bounds. So we can see the vertical line x equals 1 intersects both xe to the x squared and y equals negative 2x at x equals 1. Next, let's find our left bound. So that gives us our bound to the right. We know that the top bound of this integral is going to be 1. So let's write this down here. Next, we have to find our bottom bound. So we can see right here, it looks like xe to the x squared and y equals negative 2x intersect at the origin. However, it doesn't tell us in the question anywhere that they do intersect at the origin. So I'm going to check that they do by plugging in x equals 0 into both equations. Both give you 0 when you plug in 0. So they do in fact intersect at the origin. This means that our bottom bound of the integral will be 0. Next, we need to figure out what to put inside the integral. So, integrals can help you find the area under a curve. So for example, if we were to integrate x equals xe to the x squared from 0 to 1, we would be finding this area that I just shaded. We are, however, finding the area of this entire shaded region. So for that, we should first have xe to the x squared in this equation, because we're finding area under that. However, we also have this line y equals negative 2x, and we're finding the area above it. Since we're finding the area above it, we have to put it in as negative in the integral, so we're subtracting it from negative 2x. Because it's below xe to the x squared, and we're integrating above it. Now we have our integral, and we can start solving for the values of the area. To integrate xe to the x squared, we can use u sub. We'll let u equals x squared, so then 1/2 du is equal to x. So for the xe to the x squared part of the integral, we can now make it du times e to the u over 2. When derivating e to the x, for example, you don't have to bring anything down. In this case, we're integrating e to u, so also we don't have to bring anything down or change it. So this just becomes e to the u over 2. Which is e to the x squared over 2. Now we'll also have to add this with our integration of 2x. When integrating x, it simply turns into 1/2 x squared. So let's multiply 2 times 1/2 x squared, which is equal to x squared. Now let's add these two separate integrations together. Now that we have this, we can simply solve it from 1 to 0. This is our final answer. It can also be written as e plus 1 over 2. Let's go look at the answer key. So on the answer key right here, it gives you 1 point for writing the correct integrand. Next, you have to take the integral of it correctly. So if you messed up on the 1/2 e to the x squared part, you would lose a point. Finally, for the answer, getting the correct answer, you can write it as e plus 1 over 2 or e over 2 plus 1/2. Let's move on to part B. Now for part B, it asks us to write but not evaluate an integral expression that gives the volume of a solid generated when r is rotated about the horizontal line y equals -2. For these problems, I like to start by drawing a graph. So after drawing it here, we can see this solid that kind of looks like a frustum. There's also this cone right here that is removed from the inside. This is free space inside the volume. Now that we have a good idea of what the graph should look like, let's try and integrate it. So, from Calculus AB, you may remember the washer and shell method. The difference between these two methods is that for the washer method, you're finding the volume of slices that are perpendicular to the axis of revolution. Whereas with the shell method, you're finding the volume of slices that are parallel to the axis of rotation. In this case, we're going to use the washer/disk method because we're finding these individual radii that are perpendicular to the axis of rotation, and then we're multiplying it by pi to give us a total volume. The formula for the washer/disk method is given by this right here. Big R of x is going to be the expression that's more outwards from the axis of rotation, while little r of x is going to be the one inside, because we're not finding the volume inside this smaller area, this smaller volume right here. We're finding the volume out in here. So we're going to subtract little r of x from big R of x. If you think about it, the formula for this is very similar to pi r squared, because when you plug in a point, it gives us a radius relative to the axis of rotation. So if we plug in 1 into this top equation, we get a radius from the axis of rotation to here. However, we also have to subtract little r of x because that removes these radiuses, because we're not finding the volume inside there. The pi r squared is basically giving us the area of all these circles. However, we have to integrate it because integrating it is what gives us the total volume. Having simply pi times the r of x equation squared will only give us the area of a singular circle. If we integrate it from our bounds from left to right, we get the volume of this entire thing, because we're adding the area of an infinite number of circular cross sections together, which is what integrating does, which will give us the total volume. Now that we know how the washer-disk method works and that it's what we need to use for this, we can plug in our equations into this formula. We can use our bounds that we found earlier that go from 0 to 1. However, since we are integrating around the axis of revolution y equals -2 instead of the y-axis, we have to take into account that -2. For that, we can subtract -2 from our big R of x and little r of x inside the brackets. We can also plug in our equations for big R of x and little r of x. Big R of x is going to be xe to the x squared because it's more outwards from the axis of rotation, while y equals -2x is below. After that, we're done writing this formula. The question only asks us to write but not evaluate an integral expression that gives us the volume. So now we're done with part B. Let's look at the scoring guidelines for this. You can get 1 point for writing the correct limit and constant. You can get or miss 2 points for writing the correct integrand. That's about it for part B. Let's move on to part C. Part C again asks us to write but not evaluate an expression involving one or more integrals that gives the perimeter of R. So, to find the perimeter, we should split this up into 3 parts. We can first find the length of this vertical line x equals 1. Then we can find the length of this line y equals negative 2x. Finally, we can set up an integral to find the length of this curve y equals xe to the x squared. Once we've found all those, we can add it together for the full perimeter. To start off, to find the length of the line x equals 1, we should find its intersection points and get its y values. To find its intersection points, we should plug in x equals 1 into these bottom and top curves. So, let's first plug in 1 into y equals xe to the x squared. This means the length of this individual line is e. Now let's plug in 1 into y equals negative 2x. This equals negative 2. And since we're finding length from one point to another, we're going to subtract it and it becomes positive. Or we can also say that this line right here is 2. So the total length of the line x equals 1 from its intersection points is going to be e plus 2. Next, we should find the length of the line y equals negative 2x from its intersection points. From earlier, we know that y equals negative 2x intersects xe to the x squared at the origin 0, 0. We also know from earlier that it intersects x equals 1 at x equals 1. So, we could use arc length, but that would be overly complicated. Let's just use Pythagorean theorem. Earlier on in part C, we found that the length of this line right here is 2. We know that this intersection point is 0, 0. That means this line goes from 0, 0 to 1, 0. This means the line right here will be 1 unit long. After this, we can use the Pythagorean theorem to add them together and find the length of this line right here. Now that we've done that, we can add the lengths of these two lines together. Finally, for the last missing piece, we should find the length of this curve right here. To find the length of this curve of y equals xe to the x squared, we'll have to use the arc length formula. The arc length formula is given by this. To start off, we can use our bounds that we found many times earlier, 0 to 1. Afterwards, we'll have to find the derivative of xe to the x squared, and then plug it into our equation. To derivate this, we should use the product rule. To simplify that, we get e to the x squared plus 2x squared e to the x squared. That is our derivative. Now we can plug it in back to our integral we were making earlier. This integral right here will represent the arc length of the line of xe to the x squared right here. Now that we have that, we can add it to the lengths of the other curves that we found from earlier. And that will give us our final expression, because the question does not ask us to solve the integral, we just have to set it up. That will be our final expression. We don't have to solve this, This is fine. Let's see how this problem is scored. To start off, you can get 1 point for taking the derivative correctly. Next, you can get 1 point for writing the correct integral. And then finally, you can get 1 point for the correct answer. So most of the points you will get for this question come from the integral. That is about it for the scoring of this question. And that is it for the 2014 AP Calculus BC exam FRQ number 5. Thank you for listening.